Welcome back to Chapter 18, Part 4, Two Sample Problems where the samples are independent. Last time we talked about the MINITAB solution when we were given the data, the summary data, and this was the basic commands that you would use. In this installment of Chapter 18, we're going to see what happens if our data is in MINITAB and we don't have the summary data. This is the command we use. Instead of a 2T command, we use a 2sample command, and we tell MINITAB which columns our data is in. So we're going to look at a problem where the data is in MINITAB and use the command that you see on our PowerPoint right here to get confidence intervals and to do hypothesis tests. We're going to look at this problem, the bacteria example. Researchers wanted to determine if carpeted rooms contain more bacteria than uncarpeted rooms. To determine the amount of bacteria in a room, the researcher pumped air from the room over a petri dish at a rate of 1 cubic foot per minute, and 8 carpeted rooms and 8 uncarpeted rooms. Now, colonies of bacteria were allowed to form in the 16 petri dishes, and here's the results. We want to test the claim that carpeted rooms have more bacteria than uncarpeted rooms at a 0.05 level of significance. Now here's where two sample problems and one sample problems differ. We have to be very careful how we state our null and alternative hypothesis. By careful, I mean we have to be aware of how we set it up so that we keep our data consistent. Now, I want to test the claim that their carpeted rooms have more bacteria than uncarpeted rooms. So if I call carpeted rooms my first sample, I would have mu1 being greater than mu2. But if somehow I had uncarpeted rooms being my first sample and carpeted rooms being my second sample, I would say mu1 is less than mu2, because if mu1 is uncarpeted room, we would say it has less bacteria than carpeted rooms, which is now being called mu2. So you have to be very careful what you're calling the first and second sample. Be very aware which one is which when you're making your null and alternative hypothesis, because you want to be consistent throughout the problem. So here we have the data in MINITAB, but we only have 8 rooms, and we know nothing about the distribution. So what we're going to have to do is do probability plots and box plots for both of these. So we can go into MINITAB and write the commands. Pplot for C1 and C2 and hit enter. We'll get a look at our probability plots for both of these. And both samples look relatively normal, but we're not done yet. We have to make sure there's no outliers, so we're going to do a box plot. So we'll do the command box plots, C1 and, whoops, I should say C2. It's not going to like that one. C1 and C2, and transpose because I like them to be horizontal. So I have box plot of carpeted. Oops, I didn't get my C2. So let's just make a box plot for that one. And we see that that doesn't have any outliers either, so I can assume that my data is approximately normally distributive, so I can go about doing my problem. Now here's my commands. I say two samples C1, C2. When I write C1 first, that means that I'm saying in my null hypothesis carpeted minus uncarpeted. And remember, we said that that should be greater than 0 because carpeted rooms have more bacteria. So our alternative should be positive 1. It's a right-tailed test because that difference should be greater than 0 because C1 is greater than C2. So I'm going to hit enter, and I'll have my hypothesis test. I'll have the p-value. The p-value is 0.178. Look at my test statistic. It's a positive 0.96. Now what if I had done 2 sample, but I had done C2 minus C1? That means my alternative should have been a -1 because we're taking uncarpeted rooms, the number of bacteria, minus carpeted rooms, and our alternative says that it should be C2 should be less than C1, so a smaller number minus a larger number is a negative number, so that difference should be less than 0, which would make us have a -1 for our alternative, and that's why you have to be very careful how you set these things up. But I will still get the same answer either way. As long as you're consistent, you'll have the same result. Our p-value is greater than 0.05, so we're not going to reject the null hypothesis. The only difference is that we're going to have a left-tailed test, so our test statistic will be negative. So in your PowerPoints, I go through this whole example so that you can see it. So it's right there on the PowerPoints, the p-plot and the box plot showing that it's approximately normally distributed. Here's the commands. So, there is sufficient evidence to conclude that the carpeted rooms contain bacteria than uncarpeted rooms. So, which of the following is true? That there is sufficient evidence to conclude that carpeted rooms contain the same amount of bacteria as uncarpeted, or there is no sufficient difference between them. There is insufficient evidence to conclude that carpeted rooms contain the same amount of bacteria as uncarpeted, or there is insufficient evidence to conclude that carpeted rooms contain more bacteria than uncarpeted. Well, hopefully everybody picks. Well, you guys can tell me what you picked. Turn off and think about what the answer is. And so if you guys would, go to Blackboard and tell me what you think the answer is to that. And I'll post it. Now let's say we want to do a 95% confidence interval. Well, this would be the command that you would use, and you would get this output in MINITAB, and there's our 95% confidence interval right there. So our interpretation would be we estimate that the mean difference between the amount of bacteria in carpeted and uncarpeted rooms is between negative 1.78 and 4.61 at a 95% confidence. It's a 95% confidence interval. And as you can see, 0 is contained in this confidence interval, which shows us that the mean does in fact equal 0 sometimes. The two-sample t procedures are more robust than the one-sample t methods, particularly when the distributions are not symmetric. When the two populations have similar distributions and shapes, the probability values for the t-table are quite accurate, even when the sample sizes are pretty small, such as n1 and n2 equaling 5. When the two populations have different distribution or shapes, larger samples are needed. Now, in planning a two-sample study, it is best to choose equal sample sizes. In this case, the probability values are the most accurate. Now, why does the MINITAB output look different than our conservative method for finding the degrees of freedom? Well, take a look at this. MINITAB uses it is that they just truncate the answer, but this is how they would find the degrees of freedom. It's a pretty hairy-looking formula, so we don't have you do that. We do the approximation. But that's why their degrees of freedom end up being larger than what we do when we do our conservative method. So their confidence intervals will be more precise and more accurate. So we conclude Chapter 18. And remember, even in Chapter 18, if we don't have sample sizes of greater than or equal to 30, we need to check the data to see that both samples are normally distributed, so that we can say that the sampling distribution is normally distributed. When we had sample sizes greater than 30, we knew that the sampling distribution of the sample means was approximately normally distributed. So let's not forget all the things that we've learned in the past chapters.